Welcome back to AI Paper Podcasts. We're your technical shortcut, helping you stay right at the cutting edge of AI research.
That's right.
Today, we're really digging into a fascinating piece from Apple researchers. It's called Pretraining with Hierarchical Memories, separating long tail and common knowledge.
Yeah, this one's got some really interesting ideas about model efficiency.
Definitely. Our mission here is to unpack it, give you the blueprint, because this could genuinely be a big shift in how we build efficient LLMs.
It really tackles that, well, the elephant in the room, hasn't it? This whole issue of just making models bigger and bigger.
Exactly. Brute force scaling.
Which is hitting walls, right?
Yeah.
Especially if you want smart AI actually running on your device, not just in the cloud.
Right. So, okay, for the quick summary, the 1-minute version, what's the core problem they're solving?
Well, the problem is that current large models mix everything together, common sense, reasoning, and super specific facts into one huge set of parameters.
Which is inefficient, loads tons of rarely used stuff into memory. Think facts like, Einstein's birthday.
Yeah, exactly. Useful sometimes, but do you need it loaded all the time on your phone? Probably not. It wastes capacity.
So what's their solution?
They propose splitting the architecture. You have a small core anchor model that handles the common knowledge, the reasoning. It's always active.
Okay, the brain, basically.
Pretty much. And then you pair it with this huge, separate, hierarchical parametric memory bank. Think of it like a massive indexed library for all those specific long-tail facts.
But you don't load the whole library, right?
Right.
That would defeat the purpose.
Oh no, that's the key. At runtime, based on the context, the system fetches only a tiny relevant slice of that memory bank. Just the facts you need for that specific query.
Gotcha. And the big result, the punchline.
Okay, here it is. They showed a small 160 million parameter anchor model, plus just 18 million parameters pulled from memory.
Tiny amount.
Right, pulled from a huge 4.6 billion parameter bank. This small combo performs as well as a standard model with over double the active parameters, like over 320 million.
Wow. So comparable performance with way fewer parameters loaded at any given time.
Exactly. Huge efficiency win. And maybe even more impressively, it massively boosts performance on recalling rare facts.
Like that atomic number example you mentioned.
Precisely. On predicting atomic numbers for the rarest elements, the baseline model was terrible, like 17% accuracy.
Yeah.
Add the memory augmentation, it jumps to 83%. Massive difference for that specific knowledge.
Okay, that really sets the stage. So let's dive deeper into section 1, this whole problem of disentangling knowledge and the anchor model concept. We touched on the scaling limits.
Yeah, the standard playbook. Need better performance, more parameters. Need more knowledge, more parameters.
But it leads to this situation where, like you said, your phone's AI might be using precious RAM to store Einstein's birth date, March 14th, 1879, the paper points out.
Right, a fact completely non-essential for maybe 99% of on-device tasks, like scheduling or drafting an email.
It's wasted capacity, essentially.
Totally. So this architectural split is crucial. You've got the anchor model, they call it theta. Small, always loaded, handles general stuff.
And it learns from everything, right? It sees all the training data.
Yes, exactly. It gets gradients from all inputs, so it's constantly learning to generalize better. Common knowledge, reasoning skills.
Okay, and contrasted with that is the memory bank, $2. That's a big one.
Huge. Billions of parameters, potentially. And this stores the long tail stuff, the specific facts.
And it only gets updated sometimes.
Sparsely, only when the input data is relevant to the specific facts stored in a particular part of the memory. This is clever because it avoids catastrophic forgetting.
Right. Where learning about one topic overwrites knowledge about a completely different one.
Exactly. Because the updates are sparse and targeted, the memory bank doesn't get messed up by gradients from unrelated general tasks. It can specialize in just storing facts.
And then there's the fetched bit, tenny back.
Yeah.
The piece you actually pull out and use.
Yeah. And the key relationship is the size of that fetched memory block is way smaller than the anchor model.
Which itself is way smaller than the total memory bank.
Right.
x88 EV.
You got it. That hierarchy is what delivers the efficiency.
Okay, so that makes sense architecturally. But how do you actually build this memory bank and retrieve from it efficiently? That sounds like a major engineering challenge. Finding the right 18 million params out of billions fast.
Right. And that brings us nicely to section 2, implementing this hierarchical retrieval. This isn't just a flat database, it's structured very intentionally.
They use that DCLM baseline data set, right?
Yeah.
The big web document collection.
Yeah, 3.2 billion documents. They didn't just index it, they clustered it hierarchically.
Oh, yeah, do they go?
4 levels deep with a branching factor or dividing factor of 16 at each level.
Okay, so level 1 has 16 clusters.
Level 2 has 16 times 16, so 256.
Level 3 is 16 cubed, 4096.
And level 4 gets you up to 16 to the power of 4, which is over 65,000 clusters. Highly specific groupings of information.
Wow. And that structure maps to hardware, you were saying?
Yeah, beautifully. You can imagine level 1 clusters, the most general stuff, living in super fast RAM.
Okay.
Level 2, maybe more specific topics, could be on the next tier, like flash storage. Still fast.
And the really deep stuff, level 4.
That huge number of very specific clusters that can live on slower, cheaper storage, maybe an external disk. You only pull from there when you really need that niche fact.
Makes sense. How does the retrieval actually work then? How does it find the right cluster?
They pre-compute embeddings for all the documents using SentenceBird. Then, for a given input $6, the retriever does a greedy traversal down the hierarchy.
Greedy traversal.
Yeah.
Meaning it makes the best choice at each level without looking too far ahead.
Exactly. It compares the input embedding to the cluster centroids at each level and just picks the closest one. Its efficient only needs about 1 pk comparisons, where p is depth and k is the branching factor, much faster than searching everything.
And the result of that search is?
A tuple of indices, like I11, I2, I3, I4, telling you which cluster was chosen at each of the 4 levels.
Gotcha. And the actual memory parameters you use, the TreeXOS?
That's just the concatenation of the specific memory parameter blocks associated with each of those chosen cluster indices from level 1 down to level 4.
So you get a mix, some general context from the top levels, and increasingly specific facts from the lower levels.
Precisely. A tailored slice of knowledge for the specific input.
Okay, clever. So they had this architecture. How did they figure out the best way to integrate this memory? Section 3 looks at design choices, right? Memory types.
Yeah, they did a lot of ablation studies, testing different ways to actually implement the memory part that gets concatenated or added.
And they split their texts.
Right, and to common knowledge benchmarks, things like reading comprehension, bool Q, squad, they call this ABG-CK.
Standard LLM stuff.
Yep. And specific knowledge benchmarks, ABG-SK, things like Trivia QA, ARC challenge tasks that really depend on factual recall.
Makes sense. So what memory types do they try?
They looked at several options. A few based on LoRa, which is a popular technique for efficient fine-tuning, modifying query key or value output projections, or the feed-forward network layers.
Okay.
They also tried KV memories, which is sort of like prefix tuning, adding parameters to the attention mechanism's key value cache.
Right.
But the one they proposed, and the clear winner, was FFN memories.
FFN memories.
Yeah.
What's the mechanism there?
It works by effectively expanding the inner dimension of the transformer's feed-forward network, specifically the SWAT-AU variant they used. You basically concatenate extra parameters onto that FFN layer.
Oh, okay. Why the FFN layer?
Well, there's growing evidence that a lot of the factual knowledge in transformers gets stored in those FFN layers rather than just the attention mechanism. So they're targeting the part of the model that seems most responsible for semantic processing and knowledge storage.
Kind of like giving that part of the brain an expandable memory slot.
That's a great analogy, yeah. It's a sidecar memory that only gets loaded and used when needed for specific factual recall. And the results were clear. FFN memory significantly outperformed the others, especially on those fact-heavy ABG-SK tasks. You can see it in figure 3 of the paper.
And did the hierarchy depth matter? Like using level 4 memory versus just level 2?
Absolutely. They found that for a fixed amount of fetched memory, using parameters from deeper levels like level 4 gave bigger accuracy gains.
Which makes sense, right? Deeper means more specific, more relevant to niche facts.
Exactly. And they also confirmed the obvious but important point. Overall performance just keeps going up as you increase the total size of the memory bank dollars won. More knowledge stored means better potential recall.
Okay, so FFN memories, deep hierarchical structure. Let's get to the payoff. Section 4, the actual performance gains and deployment advantages. What were the key results when they trained the anchor and memory together?
So looking at table 1 in the paper, if we take that 160 million parameter anchor model again, when they co-trained it with the memory bank, that's row A2, they got a really solid 5.1 percentage point boost on ABG-SK compared to the baseline anchor model alone. A1.
So even a small model can learn specific facts really well with this method.
Definitely. And they saw similar nice gains for their larger 410M and 1.4B anchor models too, like plus 4.1 points on AbGSK for the 410M model. It scales.
How about that efficiency trade-off? If you have a fixed budget for parameters at runtime, how much should be anchor versus fetched memory?
Yeah, they tested that. They fixed the total runtime parameters at around 410M and played with the split.
And the sweet spot was?
It looked like around a 1-to-10 ratio of fetched memory size compared to the anchor model size was optimal. So lean anchor, more budget for the fetched facts.
And how did that optimal configuration compare to just training a regular 410M model?
This is the kicker. Their anchor plus memory model, using only about 400M total runtime parameters, like 160M anchor plus 240M fetched memory, roughly, actually outperformed the standard densely trained 410M model.
By how much?
By 3.6 percentage points on the AvGSK tasks. Better knowledge recall with slightly fewer parameters active at runtime. That's the 2x parameter efficiency claim right there.
That's really compelling. And what about speed? Latency?
This is where the hierarchical structure really shines for deployment. Remember mapping levels to RAM, flash, disk?
Right.
Loading the memory needed for a query using that hierarchical setup took them only 38 milliseconds.
Okay, pretty fast.
Now compare that to loading a flat memory bank of the same size, one giant block. Because it's so big, it likely has to come from slower storage. Loading that took 198 milliseconds.
Wow, more than 5 times slower.
Exactly. That 5x difference is huge for user experience. Makes the AI feel much more responsive.
And there's something about updates. Compositionality?
Yeah. If the user's query shifts topics slightly, you often only need to swap out the very specific deep-level memory blocks, level 4. Reloading just those deepest memories took only 47 milliseconds.
Compared to reloading the entire flat bank again.
Yeah, 198 milliseconds. So updating the knowledge context is much faster too. It's more modular.
Very practical advantages. Okay, Section 5 brings us to broader implications. Training dynamics, comparisons. You mentioned co-training worked best.
Well, specifically co-training the memory starting from an already pre-trained anchor model, row A2 in their results, was much better than trying to train the whole anchor and memory system together from absolute scratch, row A4.
Interesting. So the anchor needs some basic understanding first.
It seems so. The reasoning brain needs to learn general language and concepts before it can effectively integrate and use the specialized factual memories.
Like how kids learn language and basic concepts before they start memorizing lots of specific facts.
Exactly. They make that exact analogy in the paper, referencing child development research. Semantic understanding seems to come first, around age 3 for humans, then specific memory encoding gets much better. LLMs might follow a similar path.
Fascinating. And does this memory technique work on other models too? Or just their specific setup?
They showed it's quite robust. They took existing popular open-weight models like Gemma, Qwen, Llama 3, and just added these FFN memories after the models were already trained. Post hoc addition.
And it worked.
Yeah, consistently boosted specific knowledge accuracy across all of them. On that atomic number task, adding memory to Qwen 2.5 and 0.5b jumped accuracy from about 53% to over 90%.
Wow, okay, so it's a general technique. How does it compare to, say, RAG retrieval augmented generation? That's another popular way to add knowledge.
Good question. They did compare. Generally, their learned parametric memories outperformed standard RAG.
Really?
Well, one interesting finding was when they used the same DCLM dataset that the model was pre-trained on as the ARG knowledge source. ARGAG actually performed poorly, sometimes worse than the baseline model with no augmentation.
Huh. So the quality of the Arger data store is absolutely critical.
It seems so. Just dumping the pre-training data into a vector database wasn't effective. Maybe indexing issues or just not the right format.
What about RAG with a better source, like Wikipedia?
That did improve specific knowledge, but it didn't really help common knowledge performance. And RAG came with downsides.
Like what?
Massive storage needed 70 terabytes for the DCLM RRED index, and significant computational overhead 2.3 times the FLOPs compared to the base model just for the retrieval part.
Okay, whereas the learned memory...
Because they improved both common and specific knowledge, needed way less storage, obviously, and added only about 10% extra FLOPs overhead. Much cleaner, more integrated.
Seems like a more elegant solution.
Yeah.
And there was a point about control, privacy.
Yeah, this is potentially huge for enterprise or sensitive applications. Because specific knowledge gets mapped to specific blocks of parameters in the memory bank.
You know where the facts live.
Exactly. They showed that if they deliberately blocked access to just 116th of the memory bank relevant to chemistry,
Let me guess. Atomic number prediction tanked.
plummeted, dropped from 70% accuracy down to 20%.
So you have fine-grained control. You could potentially remove knowledge learned from a specific source by just deleting the corresponding memory clusters.
Precisely. Big implications for compliance, IP management, maybe even personalization or bias mitigation down the line.
Okay, let's try to wrap this up. To synthesize this deep dive, Apple's paper presents a pretty compelling case for pre-training with these hierarchical parametric memories.
Yeah, it successfully offloads that long-tail knowledge, keeps the core model lean, and uses sparse updates effectively.
Delivering significant gains on knowledge tasks, demonstrating really impressive parameter efficiency, that 2x figure sticks out, and offering practical deployment advantages like lower latency.
And the future directions look interesting too. They mention needing new scaling laws. How much data do you need to train these sparse memories effectively? It might be different from training dense models.
Right, TPP requirements might change.
And applying this to other areas, like vision models or handling multiple languages within this memory framework, lots to explore.
Definitely. So, to leave you, our listener, with a final thought, this architecture creates a real separation. The anchor model for reasoning, constantly learning, and the memory bank for facts, updated more selectively. Does this change how we should think about when an LLM is finished training, or when it is converged? Is convergence about stable reasoning in the anchor model, or is it about filling up that entire memory bank with every possible fact?
Yeah, when is knowledge complete versus when is reasoning mature? It blurs the lines a bit, doesn't it?
Something to chew on as these architectures potentially become more common.
A great question for the field.
Thanks for joining us for this AI Paper Podcast Deep Dive.